This episode is brought to you by Cisco Educational Premium. Did you know that the general theory of relativity is also known as Einstein field equations? These equations relate the geometry of spacetime to distribution of matter within it. These equations are analogous to Maxwell's equations of electromagnetism. Only here we are dealing with spacetime geometry. Einstein's field equations are partial differential equations. They can be written in the form G sub uv plus G, a Hill symbol thing, G uv is equivalent to K T sub mu v, where G mu v is Einstein tensor, G mu v is a metric tensor, T mu v is a stress energy tensor, and that Hill symbol is the cosmological constant, and K is the Einstein gravitational constant. Einstein field equations can be defined as G mu v is equivalent to R mu v minus half R G mu v. The term R mu v is the Ricci curvature tensor, and R is the scalar curvature. It is a second degree tensor depending only on the metric tensor and its first and second derivatives. Einstein gravitational constant can be expressed as a function of gravity. In this form, K will be equivalent to 8 pi G on C raised to 4, which is roughly equivalent to 2.077 times 10 raised to negative 43 n raised to negative 1, where we have a G to be the Newtonian constant of gravitation, and C is the speed of light in a vacuum. Einstein field equations can be expressed as a function of time. Here it is expressed as R mu v minus half R G mu v plus lambda G mu v is equivalent to KT mu v. The expression on the left represents curvature of spacetime, and each term here has units of length squared. Length 1 has units of 1 on length square. The right side represents the stress energy momentum content of spacetime. Einstein field equations work well with geodesic equation. These equations together are able to tell us how freely falling matter moves through spacetime. Matter curves spacetime, and spacetime tells matter how to move. Cosmological constant was initially absent in Einstein field equations. Einstein later added it to his original version of EFT to allow for a universe that is static. This was, however, unsuccessful as evidenced by astronomical observations. Yet the equations still work well with it. This shows that at times in life we need mistakes and imperfections to be perfect. Solutions of Einstein field equations are metrics of spacetime. These metrics describe the structure of spacetime surrounding the inertial motion of objects in the spacetime. This is successful, although the equations cannot always be completely solved since they are nonlinear. We can have exact solutions for Einstein field equations. These cases are quite surprising, and study on these exact solutions to find out what they mean is one of the current activities of cosmology. This study has even led to prediction of black holes and to different models of evolution of the universe. Einstein field equations were first published in 1915. These equations were published by Albert Einstein himself in his 1915 paper. Einstein came up with them by first obtaining field equations in a vacuum in a rather geometric fashion. After this, he obtained field equations in the presence of matter from the field equations in a vacuum. This episode is brought to you by Cisco Educational Premium. We do know that continuity equation or transport equation is consistent with Schrödinger equation. A continuity equation or transport equation is an equation that describes the transport of some quantity. It is particularly simple and powerful when applied to a conserved quantity, but can be generalized to apply to an extensive quantity. Since mass, energy, momentum, electric charge, and other natural quantities are conserved under their respective appropriate conditions, a variety of physical phenomena may be described using continuity equations. Continuity equations are a stronger local form of conservation laws. For example, a weak version of the law of conservation of energy states that energy can neither be created nor destroyed. That is, the total amount of energy in the universe is fixed. This statement does not rule out the possibility that a quantity of energy could disappear from one point while simultaneously appearing at another point. A stronger statement is that the energy is locally conserved. Energy can neither be created nor destroyed, nor can it teleport from one place to another. It can only move by a continuous flow. A continuity equation is the mathematical way to express this kind of statement. For example, the continuity equation for electric charge states that the amount of electric charge in the volume of space can only change by the amount of electric current flowing into or out of that volume through its boundaries. Continuity equation more generally can include sink or source terms, which allow them to describe quantities that are often but not always conserved, such as the density of molecular species, which can be created or destroyed by chemical reactions. In an everyday example, there is a continuity equation for the number of people alive. That's a source term to account for people being born, and a sink term to account for people dying. Any continuity equation can be expressed in an integral form in terms of a flux integral, which applies to any finite region, or in a differential form in terms of the divergent operator, which applies at that point. Continuity equations underlie more specific transport equations such as the convection diffusion equation, Boltzmann transport equation, and Navier-Stokes equations. Flows governed by continuity equations can be visualized using a Sankey diagram. A continuity equation is useful when a flux can be defined. To define flux, first there must be a quantity Q which can flow or move, such as mass, energy, electric charge, momentum, number of molecules, etc. Let ρ be the volume density of this quantity, that is the amount Q per unit volume. The way that this quantity Q is flowing is described by its flux. The flux of Q is a vector field, which we can denote as J. Here are some examples and properties of flux. The dimension of flux is the amount Q flowing per unit time through a unit area. For example, in the mass continuity equation for flowing water, if 1 gram per second of water is flowing through a pipe with cross-sectional area 1 centimeter square, then the average mass flux J inside the pipe is 1 gram per second per square centimeter, and its direction is along the pipe in the direction that the water is flowing. Outside the pipe, there is no water. The flux is zero. If there is a velocity field u which describes the relevant flow, in other words, if all quantity q at a point x is moving with velocity ux, then the flux is by definition equal to the density times the velocity field. J is equivalent to rho u. For example, if in the mass continuity equation for flowing water, u is the water's velocity at each point and rho is the water's density at each point, then J will be the mass flux. In a well-known example, the flux of electric charge is the electric current density. If there is an imaginary surface S, then the surface integral of flux over S is equal to the amount Q that is passing through the surface S per unit time. Note that the concept that is here called flux is alternatively termed flux density. The integral form of the continuity equation states that the amount Q in a region increases when additional Q flows inwards through the surface of the region and decreases when it flows outward. The amount Q in a region increases when Q is created inside the region and decreases when Q is destroyed. Apart from these two processes, there is no other way for the amount of Q in a region to change. Mathematically, the integral form of the continuity equation expressing the rate of increase of Q within a volume is as shown, where S is any imaginary closed surface that encloses a volume V. Double integral ds on S denotes a surface integral over that closed surface. Q is the total amount of the quantity in the volume V. J is the flux of Q. T is time. Sigma is the net rate that Q is being generated inside the volume V per unit time. When Q is being generated, it is called a source of Q and makes sigma more positive. When Q is being destroyed, it is called a sink of Q and makes sigma more negative. This term is sometimes written as shown, or the total change of Q from its generation or destruction inside the control volume. In a simple example, V could be a building and Q could be the number of people in the building. The surface S would consist of the walls, doors, roof, and foundation of the building. Then the continuity equation states that the number of people in the building increases when people enter the building. An inward flux through the surface decreases when people exit the building. An outward flux through the surface increases when someone in the building gives birth, a source, sigma greater than 0, and decreases when someone in the building dies, a sink, sigma less than 0. By the divergence theorem, a general continuity equation can also be written in a differential form as shown, where del dot is divergence, rho is the amount of the quantity Q per unit volume, J is the flux of Q, T is time, sigma is the generation of Q per unit volume per unit time. Terms that generate Q, for instance, sigma greater than 0, or remove Q, for instance, sigma less than 0, are referred to as sources and sinks respectively. This general equation may be used to derive any continuity equation ranging from as simple as the volume continuity equation to as complicated as the Navier-Stokes equation. This equation also generalizes the advection equation. Other equations in physics, such as the Gauss law of the electric field and Gauss law for gravity, have a similar mathematical form to the continuity equation, but are not usually referred to by the term continuity equation, because J in those cases do not represent the flow of a real physical quantity. In the case that Q is a conserved quantity that cannot be created or destroyed, such as energy, sigma is equivalent to 0, and the equations become partial rho on partial t plus del dot j is equivalent to 0, as shown. In electromagnetic theory, the continuity equation is an empirical law expressing local charge conservation. Mathematically, it is an automatic consequence of Maxwell's equations. Although charge conservation is more fundamental than Maxwell's equations, it states that the divergence of the current density J in amperes by square meter is equal to the negative rate of change of charge density rho in coulombs per cubic meter. Del dot J is equivalent to negative partial rho on partial t. One of the Maxwell equations, Ampere's law with Maxwell's correction, state as shown. Taking the divergence of both sides, the divergence and the partial derivative in time commute results as shown. But divergence of a curl is 0. So we have also but Gauss' law, another Maxwell equation, states del dot d is equivalent to rho, which can be substituted in the previous equation to yield the continuity equation. Del dot j plus partial rho on partial t is equivalent to 0. Current is the movement of charge. The continuity equation says that if charge is moving out of a differential volume, like the divergence of current density is positive, then the amount of charge within that volume is going to decrease. So the rate of change of charge density is negative. Therefore, the continuity equation amounts to a conservation of charge. If magnetic monopoles exist, there will be continuity equation for monopole currents as well. In fluid dynamics, the continuity equation states that the rate at which mass enters a system is equal to the rate at which mass leaves the system, plus the accumulation of mass within the system. The differential form is as shown, where ρ is fluid density, t is time, and u is the flow velocity vector field. The term derivative can be understood as the accumulation or loss of mass in the system, while the divergence term represents the difference in flow versus flow out. In this context, this equation is also one of the Euler's equations. In fluid dynamics, the Navier-Stokes equation form a vector continuity equation describing the conservation of linear momentum. If the fluid is incompressible, volumetric strain rate is 0, the mass continuity equation simplifies to volume continuity equation. Del dot u is equivalent to 0, which means that the divergence of the velocity field is 0 everywhere. Physically, this is equivalent to saying that the local volume dilation rate is 0. Hence, a flow of water through a converging pipe will adjust solely by decreasing its velocity as water is largely incompressible. In computer vision, optical flow is the pattern of apparent motion of objects in a visual scene. Under the assumption that brightness of the moving object do not change between two image frames, one can derive the optical flow equation as shown, where t is time, xy coordinates are those in the image, I is the image intensity at image coordinate xy and time t, V is the optical flow velocity vector. Vx, Vy at image coordinate xy and time t. Conservation of energy says that energy cannot be created or destroyed. Therefore, there is a continuity equation for energy flow. Partial U on partial T plus del dot Q is equivalent to 0, where U is the local energy density, energy per unit volume. Q is the energy flow, transfer of energy per unit cross-sectional area per unit time is a vector. An important practical example is the flow of heat. When heat flows inside a solid, the continuity equation can be combined with Fourier's law. Heat flux is proportional to the temperature gradient to arrive at the heat equation. The equation of heat flow may also have a source term. Although energy cannot be created or destroyed, heat can be created from other types of energy, for example, friction or joule heating. There is a quantity that moves continuously according to a stochastic random process, like the location of a single dissolved molecule with Brownian motion. Then there is a continuity equation for its probability distribution. The flux in this case is the probability per unit area per unit time that the particle passes through a surface. According to the continuity equation, the negative divergence of this flux equals the rate of change of the probability density. The continuity equation reflects the fact that the molecule is always somewhere. The integral of its probability distribution is always equal to 1. And it moves by a continuous motion, not teleporting. Quantum mechanics is another domain where there is a continuity equation related to the conservation of probability. The terms in the equation require the following definitions and are slightly less obvious than the other examples we have seen. One is that the wave function psi for a single particle in position space rather than momentum space, that is the function of position r and time t. Psi is equivalent to psi rt. The probability density function is as shown. The probability of finding the particle within V T is denoted and defined as shown by the equations as shown. The probability current, aka probability flux, is as shown by the equation. With these definitions, the continuity equation then reads del dot J plus partial rho on partial T is equivalent to 0, which is equivalent to del dot J plus partial psi square, the quantum wave function square on partial T is equivalent to 0. Either form may be quoted. Intuitively, the above quantities indicate these represent the flow of probability. The chance of finding the particle at some point r and time t flows like a fluid, and hence the term probability current, a vector field. The particle itself does not flow deterministically in this vector field. The 3D time-dependent Schrödinger equation and its complex conjugate are respectively as shown, where u is the potential function. The partial derivative of rho with respect to t is as shown. Multiplying the Schrödinger equation by psi with asterisk, the quantum wave function with asterisk, then solving for psi with asterisk, partial psi on partial t, and similarly multiplying the complex conjugate Schrödinger equation by psi, then solving for psi, partial psi with asterisk on partial t, we get as follows, as shown. Substituting into the time derivative of, of rho, we obtain this bunch of equations. The repletion operators del square in the above result suggests that the right hand side is the divergence of J, and the reversed order of terms implies that this is the negative of J altogether. This is shown. So the continuity equation is partial rho on partial t is equivalent to negative del dot J, which is partial p on partial t plus del dot J is equivalent to 0. The integral form follows as for the general equation. The total current flow in the semiconductor consists of drift current and diffusion current of both the electrons in the conduction band and the holes in the valence band. General form for electrons in one dimension is as shown, where n is the local concentration of electrons, mu n is the electron mobility, E is the electric field across the depletion region, dn is the diffusion coefficient for electrons, Gn is the rate of generation of electrons, Rn is the rate of recombination of electrons. And similarly for holes, we have the equation where P is the local concentration of holes, mu P is the hole mobility, E is the electric field across the depletion region, dP is the diffusion coefficient for holes, Gp is the rate of generation of holes, Rp is the rate of recombination of holes. Consider the fact that the number of electrons is conserved across the volume of semiconductor material with cross-sectional area A and length dx across the x-axis. More precisely, one can say rate of change of electron density is equivalent to electron flux in minus electron flux out plus net generation inside a volume, and can be represented mathematically as shown. Here J denotes the current density, whose direction is against electron flow by convention due to the electron flow within the considered volume of the semiconductor. It is also called electron current density. Total electron current density is the sum of drift current and diffusion current densities shown. Therefore, we obtain the equation as shown. Applying the product rule results in this final expression. The key to solving these equations in real devices is, whenever possible, to select regions in which most of the mechanisms are negligible, so that the equation reduced to a much simpler form. The notation and tools for special relativity, especially for vectors and for gradients, offer a convenient way to write any continuity equation. The density of a quantity rho and its current J can be combined into a 4-vector called 4 current, where c is the speed of light. The divergence of this current is shown, where partial mu is the 4 gradient and mu is an index labeling the space-time dimension. Then the continuity equation is partial mu J mu is equivalent to 0. In the usual case where there are no sources or sinks, that is for perfectly conserved quantities like energy or charge. This continuity equation is manifestly, obviously, Lorentz invariant. Examples of continuity equations often written in this form include electric charge conservation, where J is the electric for current, and energy momentum conservation, where T is a stress energy tensor. In general relativity, where space-time is curved, the continuity equation in differential form for energy, charge, and other conserved quantities involve covariant divergence instead of ordinary divergence. For example, the stress energy tensor is a second order tensor field containing energy momentum densities, energy momentum fluxes, and shear stresses over mass energy distribution. The differential form of energy momentum conservation in general relativity states that the covariant divergence of the stress energy tensor is zero. This is an important constraint on the form the Einstein field equation take in general relativity. However, the ordinary divergence of the stress energy tensor does not necessarily vanish as shown. The right-hand side strictly vanishes for flat geometry only. As a consequence, the integral form of the continuity equation is difficult to define, and not necessarily valid for a region within which spacetime is significantly curved, e.g. around a black hole or across the whole universe. Quarks and gluons have color change, which is always conserved like electric charge, and there is a continuity equation for such color charge currents. Explicit expression for currents are given at gluon field strength tensor. There are many other quantities in particle physics which are often or always conserved. Baryon number are proportional to the number of quarks minus the number of antiquarks. Electron number, mu number, tau number, isospin, among others. Each of these has a corresponding continuity equation, possibly including a source sink terms. One reason the conservation equations frequently occur in physics is the Noether's theorem. This states that whenever the laws of physics have a continuous symmetry, there is a continuity equation for some conserved physical quantity. The three most famous examples are 1. The laws of physics are invariant with respect to time translation. For example, the laws of physics today are the same as they were yesterday. This symmetry leads to the continuity equation for conservation of energy. 2. The laws of physics are invariant with respect to space translation. For example, the laws of physics in Kenya are the same as the laws of physics in Australia. This symmetry leads to the continuity equation for conservation of momentum. 3. The laws of physics are invariant with respect to orientation. For example, floating in outer space, there is no measurement you can do to say which way is up. The laws of physics are the same regardless of how you are oriented. This symmetry leads to the continuity equation for conservation of angular momentum. C-square educational premium is a section of C-square educationals with content that is not hosted here. There are episodes ranging from long to short videos. Remember those good old shots of ours? They are there. So do we get there? Use the link on screen or in the description or in the pinned comment below. Enjoy yourself. And I will see you in the next episode of Cisco Educationals.